Welcome, everyone. Thank you for joining our webinar today on using machine learning classification in regression models and attenuation bias, and it's given by Professor Han Zhang. My name is Tarani Chandula. I'm the director of the Methods Hub at the University of Hong Kong, and this is the third seminar in our seminar series that we have started this year. The Methods Hub aims to be the key point of contact for social science research methods experts at the University of Hong Kong and other social scientists in Hong Kong, seeking further information, resources, and training in research methods. Professor Zhang is based at the Division of Social Science at the Hong Kong University of Science and Technology. His research interests are in the use of computational social science and social network analysis methods in understanding social movements and Chinese politics. Since completing his PhD in sociology at Princeton University in 2020, he has been publishing some really innovative research using machine learning methods to analyze visual and textual data, for example, in the context of social sciences. So I'm extremely grateful that he has agreed to present some of his research today and introduce some of the methods to our Methods Hub seminar today. Professor Zhang will speak for around 45 minutes, and we will have some time for questions afterwards. So please type in your questions into the Zoom Q&A box as the seminar goes along or during the Q&A, and I will read them out at the end of the talk. If there are any burning questions you want to ask during his talk, I'll keep an eye on the Q&A box and interrupt him if needed. So thank you very much for doing this seminar, Professor Zhang, and please start whenever you're ready.
Great. Let me share my screen. Okay, great. Thank you, Tarani, for inviting me, and thank you all for the great support and help you guys give me, for turning this into reality. Okay, my name is Han Zhang, and I'm an assistant professor at HKUST. So today's talk title is how using machine learning classification as a variable in regression leads to attenuation bias, and what shall we do about it? So this topic is actually driven by my own problems I have encountered in my practice of using machine learning in social sciences. And shortly you'll see some of my own personal stories about how I came up with this research idea. Okay, so first let me motivate a little bit by, I think everyone probably have seen or are experiencing that there's a kind of increasing trend of using machine learning algorithms in social sciences, probably starting from the 2000, but for the last decades, it's probably especially salient. So I have summarized some different approaches of using machine learning in social sciences. So one of the popular approach argued by some people is like, social scientists like us should actually care more about prediction, right? If you have a regression model whose R-square is 0.01, then what's the point of it? It's not predictive at all. So this group of research argued that some problems are intrinsically prediction problems, and we should not only care about causality, we should also care about prediction. So that is one perspective. And the second perspective is getting also pretty popular in halting like causal inference literature. So that's basically, we're going to try to use machine learning to do some, predicting counterfactuals, which actually help us to do, better causal inference. And the third perspective is going to the idea of like using machine learning algorithms for variable selection, right? You have, a lot of like variables and possible interaction terms or instrument variables, or so you want to use, use machine learning to help you select some variables. Okay, so these are some of the approaches that have been used in social sciences, but it's now the emphasis of today. So this research actually focuses more on the applied side and to focus on the perspective, which is called machine learning for merriment. I think I like this term. It's a term invented by Justin Grimmer et al. In a very new article. So what this approach means is that, so imagine you have some big data set. It's maybe very large scale text or image or video or sound or network that's sort of, typical, big data that is not in a survey format. And we want to, generate some theoretically relevant variables from big data. Like, so you are interested in topics or sentiments in some text documents or images. And we can use machine learning algorithms to generate, a mirror for these variables. And in the second step, we're going to use a machine predicted, it's a prediction, but we're actually using that as variables. And you can use that as an independent variable or outcome variable in the what I call next step regression. So it's a two-step process. So the motivation is usually it's a large data size, right? So imagine if you have a data with like millions of rows of documents, right? So it would take forever for you to manually label all of them, right? So in the old days, like perhaps you are doing qualitative research, you'll be sitting in your desk and carefully annotate some of the samples and draw some conclusions. With the advent of machine learning algorithms, that typically allow us to quickly coding of the large scale documents, which give you a pretty big data set to work with, and that enables a lot of the nice things. Okay, so that's biggest motivation for this perspective, machine learning environment, and it's and a lot of especially among applied pseudoscientists, like we don't want to develop machine learning algorithms, but we want to use it, and this machine learning environment perspective is a pretty popular approach. So let me give you a concrete example, which I think this is a very clean example I can find in a recent published research by Francisco Cantu in American Political Science Review. Okay, so the problem Cantu wanted to address is what factors predict election fraud, which is a pretty big political science problem in elections. Okay, so the issue is that in the past, research can often measure election fraud at the macro level. That is, whether election at a country in a certain year or at some states is possibly subject to fraudulent election fraud, right? So that's more like a specific election level. So no one actually. So it was very hard challenge problem to measure election fraud at a macro level. And what Cantu means is like he wanted to measure like whether each vote is fraudulent or not, right? So this was a very hard problem. So the data he got is a random sample of around 53,000 images of vote tallies in 1988 presidential elections in Mexico. So this size might be larger than much larger than typical survey data set, but it's already one of the smallest big data example you can see in the literature. So this is what the raw data looks like. And from this figure, you can see pretty clearly, what Cantu means by, election fraud and what he wanted to detect, right? So essentially, he's trying to look for signs that looks like, what I just draw here, the signs of people actually intentionally, cancel out some of the old votes and, change their votes. Okay. So the research is then split into two stages. The first stage is applying machine learning algorithms. So he used very standard supervised machine learning algorithms for image analysis called convolutional neural networks. And the step he did is like he randomly sampled around 1,000 images from the 53,000, right? So for these images, he basically hired research assistant to code them into, whether this vote has some alternation signs or without alternation. And he used around 900 of them to train the algorithms and evaluate the performance on the rest 150 images. More of this, train test split later. And after he only coded around 1,000, and he trains algorithms, and he makes the predictions on on the rest of the majority of the images. And he actually found that the performance is pretty good, so he kind of stopped to code more, but instead just begin to apply his models. And in this way, he avoided the tedious task of coding all the documents, right? Sitting there and working on the coding everything. And in the second stage, that's the stage where most of the scientists are very familiar with, the next step regression stage, where he just from the first stage, the prediction stage, he got machines predicted labels of whether each vote is altered or not. Then he used this prediction as a dependent variable and have some independent variables, which is typical, what has been suggested from the political science voting theory, voting fraudulent theory. So the findings are, so this part is pretty like very much like standard through sciences, where the findings are, the votes are more likely to be altered in places where, if the polling station where the opposition party's member was not present, pretty straightforward. Or if the vote was from some Mexico states, which is controlled by governors with grassroots experiences of managing the electoral operations, so that where the holes are. Okay, so this is a concrete example of how this machine learning for measurement perspective was being practiced in social sciences. So what's the problem? The problem is that this approach is that machine learning algorithms unavoidably have prediction errors. So this is something we can't escape. Even the best algorithms have prediction errors. So for Can2, his accuracy is actually pretty high. So he already, with only 1,000 training data, he's able to get around 90% predictions correct, which is actually amazing if you have done this kind of test by yourself. But the problem, perhaps social scientists care more about is we know it's 90% accurate, but there's still 10% wrong, right? So how is this machine's prediction errors actually impacts the coefficient estimate of the next step regression, which the coefficient estimates are usually what social scientists care more about, right? To answer the question about what factors actually impacts election fraud. Okay, so this is where the computer science and social sciences actually begins to differ. Where for computer scientists, the prediction is usually its ultimate goal, right? So imagine a scenario where if you're working with a very challenging task, for instance, I think many translation problems actually belong into this category, where if the task is very challenging and say if previously the best machine learning algorithm gives you 40% accurate answer, and if you are able to invent a new algorithm that gives you 60% of the prediction correct, and that will actually be considered as a drastic or a seminal contribution in computer science, right? But if we are shifting from social science perspective, then prediction is usually the intermediate step, right? So we don't, unless your research goal is to develop a machine learning algorithm, or in most times for applied people, I think we don't actually care what algorithms you use, right? As long as it can improve the performance to make it more and more accurate, and then we potentially can better use it in the next step regression. So still using this example, imagine scenario. So if the computer scientists tell you that the best we can do is 60%, which is already a very big contribution in computer science. So can social scientists like us safely use a variable that is measured 60% correctly in a regression? I would say most people would say not, right? So the accuracy is not good enough. Okay, so this is the problem of this using machine learning algorithm as variables and just treating that as a truth in the next step regression. Okay, so now let me tell a little bit more about my personal story about using machine learning in social science research, which is actually a slightly more complex case than the Can2's example, but that helps to illustrate some of the more difficult problems here. So this is something I did in my PhD. So the goal is to, we have some data from Chinese social media Weibo, and that's all the Weibo posts that contains words related to protest. And we found this problem to be pretty hard. So this is a problem you can't, code 1,000 documents and get a good prediction. So in order to get a prediction performance, we actually wrote an article on this, and we have to use both. So essentially, we want to develop algorithm to predict whether each post is about protest or not. And we actually have to use both text and images information from a post. And then we have to, after we got this binary prediction, you're about protest or not, and then we have to merge the post, discussing the same event together. So in the end, we got around over 136,000 protests for a 7-year span. And last step, we need to generate some covariates like issues or whether the protest is valid, which also can use this machine learning. So here's some examples of the predictions we got from our algorithm. Like this is a predicted probability of discussing relevant to a protest if I show machine this images. So I think you can see like from the highest predicted probabilities, it's pretty good, prediction. But we can't simply use image alone. We need both text and images. So for instance, the left one is real protests in China. And from the text and images, we can both judge that. But the right one is actually an image. There are a lot of people gathering, and if you're just judging from the images, you probably think that this is a protest, but it's actually not. So this is actually a stampede in Shanghai's New Year's Eve, where I think one people was killed. Yeah. Okay, so basically this step is like prediction stage is very similar to Cantu. We have to get data and to train algorithms and to make some predictions on whether post is about protest or not. And in the second stage, because we spend a lot of time creating data set, right? So it's finally time to do some pseudoscience problems. And this is a problem we're encountered and trying to answer. So this is a forthcoming article where me and my co-author actually are interested in whether the number of protests impacts the number of robots. So it's arguments like if you have protests frequently occurring in some places, then the industrial, the bosses will actually have incentive to replace, to increase level of robotization to replace workers. Yeah. Okay. So independent variables are what we predicted from that previous work, right? So we have some predicted protests, and we aggregate that into the province level, and we can also aggregate that by covariates, like you have the raw number of protests, but we can also have number of violent protests or number of labor and non-labor protests. And the dependent variable is a province level robotization. This is like from survey and commercial data, so not from our predict data set. So the results are what we expected. So if there's more labor protests, then there's more robotization like a year later. But if there's more non-labor protests, so it doesn't list any significant result, increase or decrease in robotization. Okay, so how are these two examples differ? So my own research is actually more complex and have more prediction biases than example one. So let me be pretty frank, because there are accumulations of prediction errors. So like first we make a binary prediction on whether posts are relevant to offline protests or not. And then we're going to aggregate posts into the same event. And then we're going to use machine learning to generate covariates, right? Whether each protest is valid or not, which also relies on machine learning. And the last step, we actually aggregate all these binary predictions into the province level, which all the steps that can actually have some errors, right? So in our published version, which that paper was submitted a year ago, so we couldn't have solutions to that. Let me be pretty frank. So. But I think the problem is similar. So you have some machine learning predicted variables, and you insert that into the next step regression, and that exercise can actually lead to some biases. Okay, so this research addresses. You can see that was motivated by my personal research interest, because I've done a lot of machine learning and trying to use that to measure something that previously survey or administrative data cannot measure. But this research actually did the first simpler case, because I think my own regression are too complex. So it addresses a simpler case. As in the example one, the Cantu's example, where only one variable is predicted. And sometimes we use aggregation to higher level by, say, geography or time, but no like multi-state predictions. Okay, so how prevalent is this problem? So I do some like simple literature search by, I was trying to find out, actually in these three disciplines. Sorry, that's what I have been reading. So I was searching for, the articles in top journals that actually used machine predict variables in the past 5 years, and I found 18 articles. So roughly a little bit more in political science, but also 7 in sociology and 3 in economics. Okay, and 6 of them actually use unsupervised method, and actually all of them use topic models, so rely on text data. And other 12 used supervised method or dictionary method, which is actually the primary focus of this talk. Okay, and all of the 12 articles actually just inserted the predictions into next step regression as they were error-free. And actually they're not error-free, they all have some prediction errors, but all the published articles, and including mine, just insert the predictions into next step regression. So this certainly does not sound right? And later I'll tell you that this actually leads to attenuation biases. Okay, and in this talk, I just call this approach as a naive regression because that's naively treating the predictions as they were error-free, as they were the truth. And here are some interesting observations that actually pushed me to develop the method in the current format. So 8 out of the 12 articles actually use binary predictions, and the other 2 use categorical, like 3 or 4 levels, and other 2 use continuous predictions. So this talk actually focuses on binary predictions. Yeah, not only because it's simple, but also most people are actually using that right now in social sciences. And this is actually something surprising to me because I didn't expect this. So 11 out of the 12 articles actually used machine predictions as the dependent variable. And because I thought they were going to use this as an independent variable, but it's actually not. So most people use machine predictions as the dependent variable. So I was thinking like why this is the case. And here's my own rationale for this. So like people use machine learning predictions as the outcome variable, possibly because if you, this is some like textbook statistics knowledge. And I guess like for people who have taken econometrics, you're probably taught about this. So basically the textbook knowledge tells you that if you have classical measurement error, that is, the measurement error, the prediction have zero mean, prediction error have zero mean and is uncorrelated with the true value. Then we have the following 2 facts. So if you have a mismeasured independent variable, and that will lead to attenuation bias in the regression coefficient estimate. So basically your coefficient is going to be biased towards 0. But if you have a mismeasured dependent variable, that will actually give you a consistent, a good regression coefficient estimate. And of course, your standard errors will be a little bit larger, but your p-value will be also larger. But the regression coefficient, the point estimate is actually good. So I think a lot of you actually believe in this argument. For instance, I'm quoting an article that actually explicitly stated that they used machine predictions as a dependent variable because it does not affect the unbiasedness of the parameter estimate and will only make it harder to find statistically significant result. So this is actually, in most cases, this is not a correct argument. So why that is the case? Because the classical measurement error usually are working with all these like Gaussian continuous variables, but there's a argument. It's not an argument, it's a fact. Like if you have binary or categorical or bounded continuous predictions, which means like say probability is a kind of bounded prediction, which is bound between 0 and 1. So there's a fact that if you have binary, categorical, or bounded continuous predictions, that must violate the classical measurement error assumption. So basically, what you learn from the textbooks, what textbooks teach you, just does not apply to the binary and categorical and bounded continuous prediction case. Okay, so here's a roadmap of the talk. I was first going to show that if you use machine predicted binary variables, and that will give a list of attenuation biases of the slope coefficient. I mean, this is regardless of whether you use that as an independent or dependent variable. And the intercept is also biased by this. Intercept may be underestimated or overestimated. And then I'm going to talk about a series of estimators that can give you the true coefficients, correcting for machine prediction error. And I'm going to use some simulations to demonstrate the effectiveness. And then finally, I'm going to apply some estimators to publish articles. And I'm actually developing our package, so more on that later. Yeah. So basically, I have been thinking about the problem a little bit, and the literature I found is most relevant is actually pretty straightforward. So intuition is like, if we have a perspective that it's machine learning predictions, but they're actually used for measurement, right? Then there's a rich literature in the econometrics which discusses how should you incorporate a mismeasured variable in regression models. So there's a rich literature here, but the problem, or how this research and how the more general, the machine learning research and this literature differs is that so the past literature measurement error models, actually, they were developed like long time ago, right? So you really have survey and administrative data in mind, where it was very hard for people to quantify. If you have a survey data and it's already done and you can't re-ask people, right? So it's hard for you to quantify, how wrong these survey answers are, right? You probably suspect that there's some errors, but it's not easy for you to go back and check what are the errors. So literature instead developed a different way to use more complex estimators to basically make some assumptions about how wrong the measurement can be, and trying to use more complex non-parametric method to solve that. But for machine learning setting, it's actually quite different, because it is very easy, or even if you're doing standard machine learning, people actually require you to quantify the scale of prediction errors. So that's where these two parts actually differs. And later you'll see that estimating the prediction errors is actually one of the big topic here in this research. Okay, so here are some ways to measure the, as we said, the prediction errors or the performance of algorithm. So still with binary machine predictions, you have 0, 1, that's like, if you're doing sentiment analysis, that'd be positive versus neutral, or positive versus negative. So there's two ways to measure the prediction performance or prediction errors. So if you care about prediction errors, so usually the lower the errors, the better the algorithm. Then we have false positive rate and false negative rate, which hopefully after COVID people are getting more familiar with these two terms. So essentially, false positive rate is conditioning on the true values. So I use this like tilde this tilde to define the predicted value. And if there's no tilde, then it's a true value. Okay, so there are two error rates, false positive rate and false negative rate. And sometimes people also use two performance rates. So the performance is like, the higher the performance rate, the better the algorithm. So there's two values called positive predicted value, which is now it's actually conditioned on the prediction. So all of the predicted, positive documents or proposals are actually positive. So in computer science, this is also called as precision, how precise our predictions are. And we also have the negative predicted value, NPV, which is basically the precision for the negative class, for the other class. And these two quantities can actually, if you know two of them, then you can calculate the rest too. So later I will just generally refer to them as error rates. Okay, so so this section is like basically an overview of the literature, which I will quickly go over and tells you that there's attenuation biases. Okay, so the simplest case we have is actually an intercept-only regression, which just looks like there's no variable; you just have intercept. So why this is important? So so this is the simplest model, but this actually means a lot because the intercept actually is the mean of dependent variable, right? Or the proportion of the positive class. Yeah. So take Cantu's example. So intercept is actually the proportion of votes that were altered, right? So this could actually be if you are writing paper and you want to give people a descriptive statistics on what proportion of votes were altered, you can actually use this regression to get that proportion. And for the primary data, so this is the biggest data you had, and where you don't have the variables you want to measure. So you want to use machine to generate predictions, the tilde y. You don't have the underlying true labels. So the naive regression is essentially, okay, so we use predictions y tilde and to estimate the intercept, which gives you the mean, or the proportion of votes judging from the predicted labels. So we need a little bit of assumption, but essentially the first assumption requires that your false positive rate plus the false negative rate, they plus together should be smaller than 1. And this is actually a trivial assumption because imagine you have a balanced data set, half positive, half negative. If you make a random guess, and that will give you 50% chance correct. So essentially, a random guess will make FPR plus FNR to be 1. So as long as your algorithm is a little bit better than random guess, then this assumption is satisfied. Okay, so with this assumption, we can actually have an intercept correction formula, which this estimated naive is, you just like use the predict labels to run the regression or calculate the average. And that actually is related to the true intercept in the following formula. So in this case, the alpha can actually, so the naive estimate can actually underestimate or overestimate the true alpha, depending on the specific values of your false positive and false negative rate. So the implication here, which is actually independently discussed by Hopkins and Garrikin in an article 10 years ago. So they were not talking about regression cases; they just care about how can you get a estimate of the proportion of or mean of the positive documents. So the story is like you got some binary predictions, and you just take the average of these binary predictions, and that actually gives you a biased estimate of the true proportion of alternate votes. Okay, so this is the intercept formula. And now we come into a slightly more complex scenario where we begin to run regression and to add regressors into the model. And the simplest regressors, you have only one independent variable, and we don't have actually control variables. And still, for primary data, we only have the machine predicted outcome variable. So we don't have the underlying true data. So the naive regression is just regress the predicted y on the independent variable, which we assume can be correctly measured. So now we need to add a little bit assumption. This is a second assumption called non-differential measurement error. So this assumption is often the default assumption in the measurement error literature. So essentially what this is saying is that the predictions are independent of the other variables in the regression given their true values. Okay, so when these assumptions might be violated, for instance, like take Cantu as an example. So one independent variable he uses is whether the member of the opposition party were present, right? So let's imagine a scenario if people who want to, fraudsters, they worked very hard to alter ballot when the opposition was not present. So they notice this hole and they actually make it harder for you to just like alter the ballot in that case. So they essentially made the alternation harder to detect with the classifier. Then that's a case where assumption 2 will be validated. Yeah. Okay, so I think fortunately this assumption can actually be empirically verified. So the way to verify is like we have the predictions and we have some truths which we're going to talk about next. So we can perform statistical test to see if the prediction errors are significantly different across strata set by other key variables. So this is something we can actually verify. But anyway, because this is a default assumption used by most people, so I'm just using that here, but later you'll see how violation of this assumption actually makes the estimate a little bit more challenging. Okay, so with this assumption, the result is actually already obtained 20 years ago, almost 20 years ago by Jared Hausman and his colleagues. So the formula of correction is actually by this. So if you are just using machine's predicted variables to run a regression, and the regression coefficient you obtained is the left-hand side, this beta naive hat. And this one is actually equals the true value of the coefficient times 1 minus FNR minus 1 FPR. Okay, so now this 1 minus FNR, false positive rate, minus false negative rate becomes a factor of attenuation where, if the algorithm is more precise, then this FNR and FPR is closer to 0. So you're closer and closer to truth. Whereas if your algorithm is very bad and FNR and FPR both approaches 0.05, then the estimates you got from naive regression is actually very, very close to 0. Okay, and for people who have been doing machine learning a little bit, so the attenuation factors can actually be visualized on an ROC curve as a distance between the ROC curve to the 45-degree random gas line. Okay, and if we have like the predicted outcome, still predict outcome variable, but change it into a slightly more complex scenario. So previously we're running linear regression, and now we're running logistic regression. And even for this simpler case, and it's already getting too complex that no one was able to get an analytical formula for coefficient. And what we can get is only the marginal effect. But the marginal effect is still attenuated, but no one had a exact formula for coefficient. Okay, and for the predicted independent variable case, so now we assume that the independent variables are predicted, but the outcome variables are correctly measured. And this conclusion was actually even obtained like way earlier, by Dennis Agner. So the format actually looks pretty similar, but changes to the performance metric. So now, if you have predicted independent variable and you use that in the regression to get coefficient estimate, then what you get, the naive estimate, is actually the true value times the positive predicted value plus negative predicted value minus 1, which is again a number from 0 and 1. So again, your coefficient is biased towards 0. It's getting smaller in absolute size. Okay, so last, we haven't been adding any control variables into regression. And if you actually add control variables, things get slightly more complex because we don't have any analytical solutions now. But a lot of people have done many simulations, and the general result is like, unless your independent variable and some other control variables have a pretty high correlation, like over 0.6, 5.6, that sort of thing, then we still have attenuation biases. So that's a situation we have. Okay, so this part is like the literature on measurement errors, and from that we can actually know that all the previous past research, they including mine, were just using machine predictions as error-free, right? And this exercise actually leads to attenuation biases in the slope coefficient estimate. So that means like the true coefficient actually is larger, or your effect size is actually larger, which actually is not a bad news. And it's also easy to say that once we have the knowledge of the error rates, right? So that's simply the case, we already know how to obtain the correct estimate, right? Okay, but here comes a little bit tricky things, and we need one step. So by definition, we can't calculate error rates on the primary data, right? This is a big data. You don't have labels, so you want to run machine learning to generate predictions, right? Yeah, because we spend time to develop algorithms because we don't have true labels, right? So, or otherwise, why don't you just use the true labels from the primary data as variables, right? Like in Cantor's case, like if he has a true whether just each vote is altered or not, the true values, and he could just use that as a variable instead of just developing algorithms and get predictions, right? Okay, so now the solution is, especially in the machine learning scenario, is very, very straightforward. So this is where we differ from the measurement error models in survey and administrative data. So in machine learning settings, we can actually require people to have a small validation data, which we have both true labels and predictions. So if you have true labels and predictions, and recall that all the 4 error rates, or then we know the truth and we know the predictions, and you can calculate them empirically. Okay, so here's the assumptions we need. So the third assumption is basically a pretty straightforward machine learning assumption that requires that the validation data and the primary data are sampled from the same population. And the validation data should never be seen by the machine learning algorithm. So if we have these assumptions, then we can go to standard statistical learning theory and to have some theoretical guarantees that we can use the validation data to calculate error rates. And that actually gives us a good approximation of the FNR and FPR on the primary data. Okay, so let's talk about some of the issue here. So first, probably this is most this is an approach used by Cantu, for example, and for most other people. So what they do is they're essentially training their own algorithm, right? So you have some randomly coded samples from the max ledger data set, right? So that's already a random sample, and that is guaranteed to be have the same distribution as your big data. And then we can manually annotate them to create some training data. And then finally, you can hold out a small proportion of the training data as a validation data. So essentially, our data has 3 parts. You have primary data, which is ultimate data set you are going to run regression on. And we have the training data, which is used to train the algorithm, and the validation, which is used to calculate the error rates. And this is a very straightforward case. And in this case, validation data just automatically exists. We just hold out a proportion of the training data, and that's it. So this part is essentially very standard machine learning stuff. So just like the train test split idea. Okay, and for the case 2, that's slightly more difficult. Not more difficult, but we don't automatically have training data. So that would be the case if you are applying some existing models trained by others, you're doing transfer learning, or you just take some commercial, say, sentiment analysis packages and apply it on your text. And you don't actually train a model, so you don't automatically have trained data. Or you're using the dictionary method, which is also a case. Yeah, you don't train your models. Or you're using unsupervised method. In all these 3 cases, there's no training data. And a slightly more complex case, which is actually our own solution, or our own case, is we got some convenient training samples, and which is not a random sample of the primary data. Yeah. So in both of these cases, we can still have a set of validation data, and probably you should, because you need to validate how much it looks like. Okay, so the approach is you have a big data set, right? And you can still manually random sample a proportion of that and manually annotate and to say, what are to create the ground truth, which is what you're going to compare the predictions with. Okay, so these are 2 different scenarios of where to get validation data. So the gist is it's not hard. It's way easier than the typical survey and administrative data set. Okay, so once you have a validation data set, then what people usually do is to tabulate their predictions and the true values in a table, which people usually call this confusion matrix. This is essentially a tabulation of the truth and predictions. And they get the number of true positives, true negatives, false positives, and false negatives, and then calculate the 4 error rates or performance metrics. Pretty easily. Okay, now let's come into the thing where the literature actually was not touching on this. So the issue is like validation data is usually pretty very small, like often on a scale of several hundreds. Like for instance, in the Cantor's election fraud example, it actually has a validation data set with 150 observations. So which basically means that his number of false positives and false negatives are on a scale around 10, right? So that means like if you have 1 or 2 more additional data, and that can actually change his calculation of FNR and FPR quite a bit. So essentially, if you have this small validation data sets, then the variance itself may be pretty high. Yeah. So the issue is like, this is actually a neglected aspect in the measurement error literature, but I think that's something very important to address, especially because most people's validation data set are pretty small. Okay, so I'm going to propose 2 new approaches for quantifying the uncertainty of the error rates. So the first approach relies on bootstrap methods. So basic idea is to just resample the validation data set and to calculate the error rates. And to keep resampling, if you resample 1,000 times and each time you have some error rates, and we can use a resampling distribution to calculate variance and the confidence intervals, which actually quantifies not only like on average what the FNR and FPR looks like, but also how confident we're about them. And second approach is naturally a Bayesian approach, which because the number of false negatives follows a binomial distribution. That's a number of times false negative cases occur out of all false, all positive cases. Yeah. So the probability of occurrence is just FNR, so false negative rate. And all the other quantities actually are following a similar idea. So essentially we could have the real observed for number of false negatives, false positives, true positives, and true negatives, they were actually following the binomial distribution. And the probability of occurring is the 4 error matrix. And then we can use a standard Bayesian step to get the conjugate priors for phenomena. And so that's what it looks like. Okay, so essentially this part is also a different way to quantify, how varying the error rates are. So we not only care about, we not only want to use this tabulation to get a mean estimate, we also want to have a variance of the calculated values of the PVV, NPV, FNR, and FPR. And later we're going to integrate this part into regressions. Okay. I think I have to hurry up a little bit. Sorry, the time is a little bit more than I expected. Okay, so now let's talk about some different solutions to solve the problem. So the easiest way, actually, many people may not actually have thought about this, but this is actually the easiest way. So you have a validation data, right? You have some true labels in the validation data. And the easiest way is actually to just run regression on the validation data set, but using the true values, not using predicted labels. And this approach certainly gives you a theoretically good estimate, but the problem is like, the validation data is very, very small, typically very small. So it just defies the purpose of using big data in the first place, right? This is like, for Cantor, he will be running a regression on 150 observations, which basically does not allow him to further explore some of the heterogeneity here. And we think that this is actually a good robustness check for point estimate, especially if you suspect some violations or some assumptions are violated. And the second estimate is also pretty straightforward. Like in literature, we have already seen that in some early easy cases, right, we can have an analytical formula to link the naive coefficient with the true values. So once we know the values of FNR, FPR, we can just apply the analytical corrections and to get the true values. So for the slope cases, this is usually not that. I don't think it should be used because in most cases we have control variables. So shortly we're talking about that. But this intercept correction is actually pretty important because many people will actually are interested in descriptive statistics on what proportion of flows are altered or something. So this can be quite useful. And by the same logic, we can actually get the variance of the regression coefficient, which in this simple case, we can still have an analytical formula. So essentially the conclusion is that the regression, if you take into consideration of the prediction errors, so the new coefficient will be slightly larger, but the larger in scale, but the standard errors will also be larger. So, and they were actually also both by a factor of 1 divided by 1 minus false positive rate minus false negative rate. So, which basically means that if you don't have finished the statistical correction and have taken into consideration of the machine prediction errors, and the coefficient will be larger in scale, but the standard errors will also be larger, such that you basically have a larger in size effect estimate, but it's also slightly less statistically significant. So ultimately, whether the result is significant or not, depending on the relative size of the or relative performance of your algorithm. Okay, so let me quickly go over some of the more technical things, and these are actually some of the real stuff that people will be using. Yeah. So in most cases, because we have control variables, right? So we can't use the analytical corrections. So we have to use MLE, which is the standard way to solve the regression problems. So intuition is pretty straightforward. So essentially, we need to derive the likelihood function, which this part is the very standard regression. But note here that the likelihood for the observed data case is actually relates to the predicted data, right? This is actually not related to the true regression coefficient. So we have to use Bayes' rules to express the predicted data's probability as a function of true data's probability. So this is just pure math operations. And this probability, the probability of the true data, is actually related to the true regression coefficient, beta and gamma and all the other true coefficients. So essentially, we use Bayes' rules to do some operations and to link the predicted data probability to the true coefficient. So here's a detailed formula. So essentially, we need to just define what the log likelihood, what the likelihood function looks like, and then use a numerical optimization to solve the optimization problem and get the correct coefficient. I saw a question about the PBT. I think I had a working paper, so later I will send that to you guys. So you don't need to remember everything. This is pretty technical. Yeah, I think I hope you get the intuition, but you don't need to remember all these formulas. This is just yeah. I think intuition is probably more important than how detailed what this formula looks like. Okay, the fourth estimator actually relies on bootstrap method. So we have an MLE, and we can use MLE to get a good estimate of the coefficient. And to further incorporate the variance of the error rates into the, because as you can see, this MLE actually relies on the values of FNR and FPR, right? And as we said, FNR and FPR can have high variance. So what we're going to do is essentially incorporate this variance of FNR and FPR into the final regression coefficient estimates. So the bootstrap essentially is going to take following what our estimation of the variance of the error rates into consideration, and repeat just keep reshuffling the validation data set and calculate the resampled error rates. And use the resampled error rates in the MLE to obtain one set of regression coefficient. And you can do this like say 1,000 or 10,000 times, and you have 1,000 regression coefficient estimate. And then you can apply standard like mean, standard deviation, or quantile functions to get the average and standard errors and confidence intervals for all the steps. Okay, so this is what Bootstrap adds onto MLE is to that Bootstrap treats the error rates as varying, as MLE just treats the error rates as a fixed quantity. So the Bootstrap should give us a more conservative estimate of the confidence intervals, such that you basically get a more robust result. Yeah. And the Bayesian part is still the similar idea. Yeah, we're extending our, error rates, the variance of error rates part into the regression analysis. So this is basically a pretty standard, it's actually a mix of third components. The first component is the variance of the error rates, and the second component is the likelihood function we got from the MLE. And the third part is just the standard Bayesian's logistic regression setups. Yeah, as I'm going to omit the details, but let me show some results. Yeah. Essentially, the Bayesian and Bootstrap are all ways to incorporate the variance of the error rates into the variance of the regression coefficient estimate. Okay, so here's some simulation result. So first I simulated data set. So this is a case where we actually know what are the true values are, and we just artificially generate some predictions, and we say whether our proposed estimators can recover the truths. And I actually selected a pretty small validation data set. So which, as you can see, that's roughly on the same scale of Can-tooth to say, if validation data sets as small as 100 can actually make an impact on coefficient estimate. Okay, so here's the simulation result. So as you can see, the naive regression, which is the first column, actually underestimate, in all the cases, underestimate the true coefficient values. Whereas all the other four different approaches actually give us a good estimate. And in this predicted outcome variable case, the Bayesian estimator actually gave a smaller standard error than the Bootstrap. And the reason is that, so now we're moving from the plot from the regression coefficient to the density distributions of the error rates. So under the Bayesian approach, the Bayesian actually gives a slightly smaller variance, like here, the confidence interval of the FNR and FPR are tighter than what it was provided by the Bootstrap method. And that's a reason why, in the coefficient case, the Bayesian approach has a narrower confidence interval than the Bootstrap method. And the situation is reversed if we have predicted independent variables. So this part is basically similar, but for the predicted independent variable, the Bootstrap method actually gives a tighter confidence interval than the Bayesian approach. Yeah, and again, the naive estimate actually are at least away from the true values for the intercept and also for the regression coefficient. And the second one, this is validation data. So as you can see, the validation data regression actually gives you an unbiased coefficient, but because the size of the data set is pretty small, so the confidence interval is pretty wide. Okay, so here's some additional simulations. So for instance, one practical question is the size of validation data set, like how large you should select your validation data sets to be. And here's how the standard errors of the coefficient actually changes by the size of validation data set. So basically, as you see, that when the size of validation kind of reaches around 500, then the gain in the reduction in the standard errors actually becomes not salient. So that's roughly more than what Can-2 used, and probably more than many people have used. Yeah. And here are some plots for the allowed error rates. So rationale is if you have FPR plus FNR, which is smaller than 1, this is a minimum requirement based on assumption. But the issue is we not only care about point estimate, right? We also care about variance. So I'm just basically plotting the FNR plus FPR by the coefficient. And the conclusion seems to be that if your FPR and FNR, if you sum them together, and that's larger than 0.07, then the standard errors become so large such that we can't effectively distinguish some estimate from the naive estimate. So that's probably a rule of thumb scenario where you actually should improve. Like say if your machine learning algorithm's performance is this bad, then you probably should focus on improving your algorithm first instead of just using that in the next step regressions. Okay, so here's some last result. So as I said, we actually assumed a non-differential merriment assumption, which is basically the merriment error is independent of the other independent variables. So now I'm letting the merriment error and the other independent variables to be correlated as the x-axis shows, and to see how the regression coefficient actually because this is actually a scenario where the violation of assumptions of the estimator is violated. So I don't guarantee that the estimators will give you a good unbiased estimate. And as you can see, in some cases, the estimator still gives reasonable but still biased estimates, which is expected. But the point I want to make is like, this is a slightly more challenging scenario. And if you look at this one, like this. So these are the naive regression. And the point I want to make is like, under this violation assumption, the naive estimate, and this is what people have been doing, always in the applied research. And in this more challenging scenarios, the naive regression is likely way worse than all the other approaches we have been discussing. So I think this can be a future direction, but now the conclusion seems to be that, so we know the assumption is violated, so I don't guarantee that the estimator works. But even under this scenario, the naive regression, which is what people have been using, is actually way worse than estimators we have been discussing here. Okay, so finally, let's come into some of the, using our estimators to revisit some of the published articles. This is a kind of example we have been seeing throughout. So the naive is what he offered in the original article. Yeah, this is a regression coefficient estimate in the original article, the red one. And after applying several different estimators from mine, so usually the expected result is like, you get a larger in size coefficient estimate. And also the confidence interval gets widened. So, but in this case, his performance of his algorithm performance is actually pretty good. Yeah. So such that the results still stays statistically significant. So which is actually not a bad thing if you think about this. So basically you get a larger effect size, right? So you get more things to talk about. And the result is still statistically significant. So that actually makes your study stronger. Okay, so this is a good case if the machine's prediction is pretty accurate. Yeah, so interpretation doesn't change, but the effect size actually get larger. And this is an example where I think the solution gets slightly more tricky and the original conclusion might not necessarily hold. So this is also a new article by Katagli and Min in 2019, also in APSR. So the authors are interested in investigating, so let me list their variables. So essentially their dependent variable is White House willingness to use force to confront the Soviet Union in Berlin. So this articles, have a context of Berlin crisis in mind. And the two predicted independent variables are, whether the U.S. Department of Defense trying in their telegrams, they expressed willingness to use force. And the other independent variables, like whether the Foreign Broadcast Information Service is represent journalists, they showed willingness to support the government to use a military force to confront the Soviet Union, right? And this is a more complex case because this study actually have both predicted dependent variable and predicted independent variable. So that's more complex than Cantu's case where only one variable is predicted. And the third variable is not from machine learning. So this is coded by expert. It's New York Times, like public information. Yeah. Also, like whether New York Times like columns supported use of military force or not. And this article is not only more complex in this, in the sense that both the outcome and independent are predicted, and it's more complex because they actually aggregate their data into so let me go through it. So they first train an algorithm to classify whether all these documents expressed willingness to support to use military force, right? So this is a binary prediction at the document level. And then they aggregate this document level predictions into the weekly count of document expressing willingness to use force, right? So previously you have each document is supported or not. And now you have like within each week, how many number of documents from different sources supported willingness to use force. So essentially they're turning a binary classification to a continuous count. And this is also used like, in my own research, whereas I aggregated by geography and they aggregate by time. And that's also a common way of how people have been using, this kind of binary classifications. So this is a time where the intercept correction formula is useful because, if you have the weekly count, then you can use a mean to times the number of documents in that way to get the, get the weekly count of documents belongs to a certain class. So I basically use the intercept correction formula to obtain the corrected means, and which actually relies on assumption that is the machine learning algorithm classification rates does not vary by time, right? So because they have like several weeks, several months data, and you have to make the assumptions. And unfortunately, I was not able to verify this assumption also because their current replication data basis validation data is around 150 to 300 size. So within this small size, and you imagine you further cut that into say 8 weeks, and you only have like 20, 30 observations within each week. So we just cannot get a meaningful calculation of what the error rates looks like for each week's classification. So unfortunately, we have to assume that the error rates are constant across time. Okay, so here's a corrected result by adding that constant error rate assumption. And so the new estimates increase the scale of coefficient. So the red one are still his own original estimate, and the green ones are my own estimate, new estimate. So as you can see that in this published article, the result is already kind of borderline statistically significant, right? It's pretty narrow. And once we have taken into consideration of the machine classification error, and that makes the effect size slightly larger, but that also increases the standard errors such that now like this one is no longer statistically significant. And also this one is no longer statistically significant. So that basically means that many of the conclusion in that original article was actually, or after we revisit this study by taking into consideration of the machine classification error, and the original conclusions may not hold anymore. Okay, so last, let me talk about some of the observations. So first is still going to the the example we just talked about. So this is an example where people first generate binary predictions at the document level and then aggregate that into, say, by geography or by time, right? And this is a slightly more tricky scenario because the naive approach certainly is not correct because that doesn't take into consideration the error rates. And currently, I'm working on the assumptions that the error rates are, constant across time or across provinces, geography. But I think this is sort of like an open problem. Just imagine, like, if you have 300 like data rows and you want to have estimate error rates for each of the weeks. So that's basically a very hard problem intrinsically. And another observation, and so far, since you have been hearing me talking about also the supervised staff and dictionary method, and you probably noticed that I have been talking about, especially topic modeling, this kind of unsupervised method, right? So typically, it's not an easy task to generalize the idea of validation data to unsupervised method, probably because it's also a little bit hard to define what is the ground truth in unsupervised cases, because there probably are not ground truths, right? So this is slightly different from the unsupervised machine learning case. Yeah. So essentially, I think this is another open question and direction. So this is not to say that you use topic modeling, so you automatically are avoid of the problem discussed in research. So still, machine predictions can have variance and problems. Okay, so I think one of the similar work following the spirit of this research is structured topic models, which some people might have been using that, in this audience. So essentially, the problems they want to address is like, okay, imagine like you run a topic model and you find out that this document is about 80% about economics and 20% about geography. And if you want to use this 80%, 20% as variables in regression, and you have to take into consideration of the variance of this 80% into the next step regression analysis, which is something where the structured topic models share the similar spirit of this research, in the sense that we both want to address the issues of machine learning's prediction errors and prediction uncertainty, but we can use a different approach. Let me quick wrap up. So essentially, the conclusion is like if the binary machine learning predictions are directly used as variables, in the next step regression, then the slope coefficient is typically attenuated, regardless of whether the predictions are used as independent or dependent variables. And the intercept can be underestimated or overestimated. And we proposed a series of estimators to obtain consistent estimate of regression coefficient. So these are the 5 different approaches we discussed. And after correcting for machine learning's prediction errors, and the new coefficient will be larger in scale, the standard errors will also be larger. So it's a trade-off between larger effect size and more larger standard errors, and depending on the relative performance of accuracy. So sometimes you get a stronger result, and that's also statistically significant, which is good. But if your machine learning's performance is not so great, then it probably will goes into a scenario where you actually cannot get a statistically significant result. Yeah. Okay, so here's some next step we think falls pretty naturally following this article. Like we can address issues of the violations of the independence measurement error assumption, and we can deal with the categorical and continuous prediction case, and also do more work on the aggregated binary prediction case. And the last case will be, the validation data are coded by humans, right? So what if, you have several coders and they don't agree with each other? So all this kind of intercoder disagreement issues. But in general, I think that this is probably where, as you can see, the computer scientists and our social scientists actually begin to differ, where computer scientists actually, I don't think they care about this kind of problem, but the direction I'm talking about in this talk is actually what social scientists care about, how to get a good coefficient estimate of the regression. So I cannot believe that this is actually have a bright future when more and more people have been using machine learning in their own research. Okay, so this is the end of the talk. And as I said, I have a working paper, which I think I'm going to update like in 1 or 2 weeks. And I'm actually developing our package. It's not very mature, but it's, yeah. The semester is over, so I have more time to write codes, and that's great. Okay, so if you have questions, suggestions, and yeah, just feel free to raise it here and or also email me. I'm terribly sorry because I think I'm going super over time. Yeah, yeah, but that's the end of the talk. Yeah.
Thank you so much, Dr. Zhang. It was really wonderful to hear all that detail, which is it's really important. But also your your personal stories about how you've come across these methods, how they've been used in previous research. So thank you so much. So there's time for some questions, and there already are a few in the Q&A. So we've got one from Calvin that's asking about what's the number of samples required for the training data set and the validation data set. So in standard sort of power calculations, we usually estimate the required sample size to do some research. Is there some idea about a typical sample size needed for machine learning, like 400 to 500 samples for validation?
Yeah. That's a great question, and I think this simulation result is is a first step towards that. But I think what you propose is a very interesting. Yeah, what I'm talking about this. So this is my kind of intuitive answer to your question, where I'm just varying the size of validation data and seeing when the standard errors of the coefficients stops to decrease. But I think your suggestion leads to a more formal solution to this problem, which I don't have an answer now, because as you can see, this is a very new direction, and probably because most of the previous people in measurement error, they don't discuss this kind of problem. But I think this is a very good suggestion, and I will write it down to see if I could do more formal work on this direction. Yeah. I agree with you. It's just I don't have a good answer now, but it's a good direction. Yeah.
So we've got a question from Dodo. So thank you for a very inspiring talk. I have a very general question. As far as I understand it, prediction bias is simply inevitable in machine learning. So, and it's likely to cause attenuation bias in data regression analysis. So is there a rule of thumb that when the prediction bias reaches a certain threshold, we should use your proposed estimators to obtain consistent estimates?
Yeah. Mm-hmm. Yeah, I think that refers to this slide. Sorry, I think I went a little bit too fast on here. So essentially, if you want to get a theoretically unbiased estimate, then the assumption is actually very minimal. So assumption is just so this should be FPR plus FNR is smaller than 1. Where a different way of saying this is you have to be slightly better than random guesses. Yeah. So that's a minimum requirement if you want to get a good point estimate. But if you want to get a reasonable confidence interval, you don't want to blow your confidence interval. Yeah. Because my sense is if you have FPR plus FNR to be say 0.099, which is a very, very bad machine learning algorithm, just a little bit better than random guess. And in that case, you can still get a theoretically good point estimate, but I guarantee that your confidence interval will get, you will basically blow up, and you just cannot get a meaningful statistical hypothesis testing in any sense. So again, this is more like an intuitive rule of thumb, and I think I need more work on that. But that's basically the rule of thumb I have explored right now. So that's you essentially have to have algorithms whose false positive rate plus false negative rate together should be smaller than 0.07. Yeah, that's a rule of thumb I identify from my simulations. Yeah.
It's great to hear rule of thumbs. Yeah, it's really useful especially for those of us who are new to the field. So I've got a next question. I'm not sure I completely understand, but it's suggesting that you're looking at the tradition of measurement error studies. So an alternative method is to look at multiple imputation, which might be more consistent with machine learning. So I'm not.
I think I probably get what Kenji is saying. So intuition is let me say it in my way to see whether I got your understanding correct or not. So essentially, this multiple intuition might be saying about this, but if my understanding is correct. So for instance, now my approach is just to do the tabulation and get the empirical, proportions as a way to estimate these 4 error rates. But if we're following the multiple imputation approach, then we can essentially construct a regression. The outcomes is still this error rates. as independent variables can be all the other confounders in the regression, which is supposed to be a better way to account for the violation of a differential merriman error assumption. Yeah, that's my understanding of the question, but I don't know whether I get it correct or not. And I think that is indeed a way to proceed. Yeah, I've been thinking about this, and that's I think that's a good one, and that's actually a natural direction I'm thinking to be going.
Yeah, it's really interesting to get these ideas of coming from different sort of methods and approaches. So yeah,
it's actually interesting because some of you might know my background is actually from computer science, so I'm actually self-teaching myself into all this Merriam error stuff. Yeah.
So I've got a question from Kinghua asking about endogeneity. So I see right at the start you mentioned the use of machine learning methods in causal inference and so on. So Kinghua's asking, is endogeneity an issue in this regression? So if the machine learning error is correlated with the error term of the regression model, could this be an issue?
Certainly. Yeah, I think I forgot to mention this in the last slide, but that's certainly a pretty important issue. Yeah. So let me say it in this way. So if we look at this, the endogeneity can actually be expressed in these assumptions. Let me see. Sorry, where's my assumption? This assumption 2. Yeah. So this assumption can actually be expressed in 2 ways. So one way is like the violation of the assumption. The prediction errors are dependent of some other variables, but you can measure that variable. So that will be the case where we're essentially selecting on observables, right? So that's why I said multiple imputation case, where we know the prediction errors are not random, but we know what confounders can determine that. So we can somehow use these observed confounders to predict the prediction errors and to somehow make it, essentially that's like a selection observable type of argument. But I think Kinhua's case is slightly more complex, because expressed in the violation of this assumption, we can understand that as a type of unobserved confounder case, where we know the prediction errors are dependent of some unobserved confounders. And that could be due to the selection process. For instance, like in creating the training data, we artificially discard some data or add some more data or oversample some data. And if you not fully control this kind of selection process, and that could actually lead to a more complex scenario. And I think in my draft, actually, sorry, I haven't uploaded it to the archive, but I will upload that within a week. So I think I did some additional analysis on the unobserved scenario, unobserved confounder case, where it is a case that you have more selection bias or more endogeneity issues, then the estimators will have more bias. Yeah, but the story is like the naive estimate is even worse. You have endogeneity problems. That's my way of saying that you probably should not, if you suspect super high endogeneity issues, then my recommendation is like you should not use naive regression, because naive regression will give you even higher biases. But I also acknowledge that my assumption is also, because my estimator relies on this assumption. This assumption is violated if you have endogeneity issues. So my recommendation is actually to compare, what my estimator gives and the validation data only, because this will be a very extreme case. And I think the best we can do is like, you maybe get a slightly more validation data and to try to run a regression on maybe several hundred observations and to get a reasonable point estimate. So that may not give you a good confidence interval, you get a too high confidence interval, but at least the safest way is to actually rely on validation data. Yeah, I would say so. Yeah, that's a very difficult problem, and as you can see, that's certainly something I need to address later. But so far that's the best I can suggest I can give.
Got somebody with a few questions, so I'll take one of them. So besides treating machine learning methods as variable generators, is there any study in social sciences directly applying machine learning to conduct prediction? And what's the quality of such studies?
Oh yeah, that's actually what I said in the very early beginning. They already have a different framing, so the basic frame that we need to pay more attention to the predictions. Yeah, especially I like this article by John Timberg et al. So they basically frame some question as an intrinsic prediction problem. So usually I think it would be easier to frame a policy problem as a prediction problem. So for policy problems, you don't only care about, like if you have a causal answer, but that causal answer is like not predicted at all, so probably, yeah. So that's a slightly different angle of, it's not the same, it's not the same angle of this approach, but that's a different approach. Yeah, so you can look for some of the citation I have, especially this perspective one, so to look for more studies that follow that approach.
Thank you. And just as a reminder, so this talk is being recorded, so and we'll put it up on the Methods Hub website, which will go live hopefully next month. So all of these references and so on will be available. It's getting to 12:30 now, so I just want to maybe ask one or two more questions before we let you go. And thank you for the great talk. So the next one is about, if we apply machine learning methods to generate variables, do we need to compare the performance of these methods with conventional methods like linear regression, clustering methods, and so on? So I'm guessing the answer is yes. I mean, that's what you're doing with your simulations when you're comparing the different methods, aren't you?
Mm-hmm. Let me see. I think he or she is asking a slightly different question. That is like, if the goal is to generate variables, then should we, compare the more than like machine learning versus linear regression clustering? Yeah, I would say you can try as many methods as possible, but ultimately, for applied researchers, I think the way to determine is that you should have a validation data set, and I mean, each algorithm has their own strengths and weaknesses, theoretical strengths and weaknesses, right? But the ultimate decision should be based on, you should choose an algorithm that generate the smallest error rate on the validation data set, right? So I think that's actually the principle used by standard machine learning people, right? So because we know like deep learning have good and bad, we know like linear regression have good and bad, but because the first stage is essentially a prediction stage, so you should essentially reduce a prediction error in the first stage, and that's where the validation data comes in and becomes handy. Yeah. I think that's what his or her question is asking.
Great. It's gone 12:30 now, so, and I don't want to keep you for long. So thank you so much once again for doing this wonderful talk. As I said, a lot of great detail, a lot of wonderful sort of very nice explanations about introducing the audience to these methods, and really interesting development. About trying to incorporate the variance, these prediction errors into the model. So I really look forward to reading the published papers soon and hearing more about your research. So a very big thank you to you, Professor Jang. Thank you.
Great, thank you so much, and thank you for the organizing. Thank you for all guys coming. Yeah, and if you still have any questions, I know there's several questions lying there, so just feel free to send me an email, and we can continue the conversation.
Great, thank you. Thank you. Bye bye.
Great, thanks. Bye bye.
Bye. Bye everyone.